Hello again. Today we're going to look at seeing how we can actually sort of draw a distorted mesh for our springs that we made earlier for the grass. We'll also be looking at how to make a tail move around. Something a bit like this. Since we're in the tail code at the moment, I may as well show you how the tail system itself works. So I've got an array of bones here. This just keeps track of the mouse position. And this is just the source image on the rectangle. We can set the size of the tail. Down here in initialize, we get the image for the tail. And we make 5 bones, we allocate them, and we set them to a tail size. So if we go over to the tailbone class, it's actually really simple. There's a position, a velocity, and a target length. So when we constructed the bone, we set the target length. If we don't specify anything, it puts it at 30. When we run the update, we specify what we want that particular bone to follow, which will be the mouse position. The X bias, which is sort of a directional bias, that determines which way the tail will try to point. So if the character is pointing left, then the X bias will determine the change of X velocity for the bones inside. And that'll make it so that the tail will try to point in the opposite direction the character is facing. There's also this horizontal bias here. For each bone, when it loops, the horizontal bias will be a bit different, so that the tail arcs downwards a bit. A strong horizontal bias will cause the tail to point outward, almost straight out. If we set the horizontal bias to 0, that part of the tail will point straight down. We get a toward vector, which basically is the vector that looks from the position of the current bone node, the position where that bone starts, and it looks towards the previous node. In the case of the first bone, it would be the mouse position. So what it does then is it calculates the distance along that vector. We can use the distance along that vector to figure out if it's too close or too far. What this calculation here does is this gets the direction that that vector points, that points to the previous node, and it makes it the length that we want each vector to be, which was that target length that we passed in here. So that's the size of each bone. So this here would create a segment that's exactly the right length that points in the direction towards the previous node. And so what we do is we go to the previous node, which is right here, and we subtract that vector to go backwards from it along that vector. So we're kind of backtracking to get to exactly where we'd like this to be. But instead of just setting the position to this right here, what I'm doing is I'm making it so that it's going to be 70% this and 30% what it was in the previous frame. You could adjust these depending on how you'd like it to behave. Also, in here we add some gravity. What we're checking here is if the position that it's at right now, minus the previous node, so if the vertical difference between this node and the previous node is less than the target length. So if you imagine if it was pointing straight up and straight down, we don't want to add gravity when this distance is larger than the target length, because if it's pointing straight up and straight down, the furthest down it could go is that target length. I subtract a horizontal bias here so that if we want it to be more horizontal, it reduces what this target length would be. So in other words, we don't want it to go too far down. If it's not too far down, then we're allowed to add some gravity. The next line is exactly the opposite. If the position causes the length between the two to be so far that we know that it's definitely too far down already, then what we do is we actually reduce the gravity on purpose. So we put the brakes on. So here we're passing in a directional bias based on which direction the character is facing. If the character is facing in a direction such that it's less than 0, then we want the tail to go to the right. So we let it migrate to the right by giving it some horizontal velocity towards the right. If it's greater than 0, then we have it go to the left. Now keep in mind, this isn't going to go too far, because this thing right here is always trying to correct it so that it's 70% of what it should be for its distance to the previous node. Also, right here we slowly reduce the velocity. If there isn't much happening, the velocity will come down fairly quickly. And we adjust the position based on the velocity. So an update, this may take a little bit of explanation. I added this isn't necessary. You could take it off of yours if you want. I added this constant float tail wave size. We could actually even reduce this. We could say that it's 0.8f, for example. And the waving of the tail when the character's not moving is greatly decreased. If we wanted to move a lot, we could say 2.8, for example. That's a bit too much, causes a lot of distortion. You may have to tweak your values to suit the tail and the tail thickness that you have for your character. This is just a very small helper method. All it does is it takes an integer, which is the index when it runs through this loop for the bones, and it uses that index as sort of like an offset or rotation amount. So what it's doing is, as it goes through each link, it's using that index, and we're timesing it by 0.1 to make it much smaller, so it's sort of a radian value, a corresponding radian value. And we're kind of adding it onto our regular rotation right here, which is updated every frame by 0.1. This isn't absolutely necessary, but if it goes larger than 360 degrees, which is 6.28, then it just loops it. Even if we didn't have this, it would still loop it with the way it works internally. That keeps updating here, and so the sine wave will wave up and down based on this value as it continues to cycle. And we scale it because it normally scales. This normally is a range of -1 to +1 as it waves, and so we scale it by the tail wave size, which is right here. You may also want to consider that this is added every frame, so you don't want that wave size to be too big. I'm keeping track of the last X direction, horizontal direction, and the purpose of that is if the player is facing a certain way, we want the tail to try to drift the opposite way. And you could do the same thing with ponytails or hair, and the same algorithm would apply, although you'd probably want to take out this line here if it was a ponytail. Not just that line, this line here too, unless you wanted to add a little bit of subtle wind. And with the way that this resolves it, and I don't have it doing multiple loops to sort of stabilize it like you would with Verlet Integration, it does almost look like there's a little bit of wind going through it, which I kind of like, so I left it like that on purpose. The horizontal bias that's sent in is kind of giving the tail a bit of stiffness with each bone, and that's why it kind of holds it at an angle. So that's this H bias that's passed in, and that determines how much that tail is kind of pushed to the side. So the initial H bias is 9, and as it loops, it decreases the H bias for each link in the chain by timesing it by 0.5. We could make it decrease the strength even faster if we went by 0.2, in which case it would droop further down. I think 0.4 would probably be a good value to use. I'm going to turn the waving back on. Right here we're getting the difference between the mouse's position and the mouse's previous position, and storing that as xdiff. If it's not 0, we store the last non-zero value. We need a non-zero value to determine, to pass in xdir, so that it can determine which way it wants the tail to point. So if the character is facing left, it'll know that the last non-zero was the character facing left, and it'll use that to make the tail point in the opposite direction. When it loops through the bones, we start at 1, and the reason is because we did 0 here, and the reason we did that is because we're attaching the first link, the bone 0, to the mouse position. And normally we'd use the hero's position somewhere on the butt of the hero, or if in this case it would probably be a fox-like creature. So then we loop through these, and we started at 1, and we're looking toward the previous node each time, and trying to adjust our position to be a certain length, a certain distance from the previous node. After all this is calculated, that's when we actually add this wave value in. And with each link, like I said, we're decreasing the amount of influence so that it arches, the amount of horizontal influence. And down here we call a QuadBatch.drawTail, and this is using my QuadBatch, so it allows you to distort the vertices. So we'll go take a look at that and how that works. The parameters we're passing in here is the source rectangle, the color, the starting position, which would normally be the hero's position, and the list of bones. We have the option of scaling it, so say 1.3F, maybe make it a little bigger. With this tail being as thick as it is and the links being as short as they are, distortions will be more likely to show up. So to avoid that, I would use just a scale of 1 or even 0.8F, slightly smaller. That scales it vertically. So this particular system, the way it works is the scaling is only, well, the tail has to be on the sprite sheet so that the base of the tail is to the right and the tip of the tail is to the left, and it's facing horizontally on the sheet, preferably filling most of the rectangle, and preferably not too thick. In this case I'm going to go 1F. Alright, let's go to the QuadBatch drawtail and see how that works. So just to refamiliarize you with QuadBatch, you can skip this part if you're already familiar. It kind of works like SpriteBatch, and it sets up a 2D orthographic off-center style camera. There is a tutorial on QuadBatch in the platformer series that you can check out if you want to learn more about that. We're just going to go to the specific part on the bottom down here about how to draw the tail. To kind of visualize what it's going to do is we got this source rect like this, and so what we need to do is we're starting from the right side and working our way to the left, and we're doing it in chunks based on how many joints we have. So if we have just 4 like we do right now, I think we're just using 4, so it'd be 1, 2, 3, and 4. What we're going to try to do is, first of all, we figure out what this joint is, which will be bent in some direction. Same with this one. These aren't actually going to be straight, so there's going to be 4 of these joints combined. We're going to need to figure out this and this one, and this one. And then once we've found these, keep in mind that this joint here could be like that, and the next one could be like this. And so here's the problem. The problem is this will be like this way, but then this one here will be this way because it runs perpendicular to this one. So what we'll do is we'll average these points here, like so. After we average them, this will be 1, that'll be 2, that'll be 3, and this will be 4. So then we'll connect them like so. And then we go to the next one and we do the same sort of thing, and we might end up with something like this, where this will be 1, this will be 2, and so on. So when we create the quad, we're going clockwise here, and it's going 1 to 2 to 3. So 2 and 3 are vertical to each other, which could make it confusing, and then to 4, and then to 1. So 1 and 4 are actually together. Something you'll have to keep in mind if you want to understand how it works. The UVs, this will be U1, and anything along this line will be V1. Anything along this line will be V2. So that's where on this sheet it's actually going to try to extract from based on where it starts at this vertice and interpolates across to get to this vertice. U2 is to the right here. And this is probably impossible to read. So U2 is to the right and U1 is to the left. And we're going to divide this up by how many there are. And we're going to say that U1 is equal to, U1 would normally be over here. So we're going to say that the U1 starting in this loop is going to be equal to U2 minus the original U2 minus U1 divided by 4, because that's how many sections we have here. And then each time it goes through a link, it's going to say U1 minus equals the U division amount. And it's going to go so that it starts here, and it'll do the same with the U2. And it'll start there and end here. So not that it's essential to understand how this is working, but if you are interested in understanding how this is working, this might help a little bit. So we'll take a look at the code then and see what I'm talking about. So we'll just take a look at this add quad thing here first. When we add the 4 points to make those quads like I was showing you, this is the top left, top right, and bottom left. And same with the U1, V1, those are on the top left side. So for the first vertex, we're going to use the top left. For the second vertex, which is on the right side, we use U2 because it's to the right, but we're still using V1 on the top. And for number 3, bottom right, we're using the bottom right UV coordinate here. And same with bottom left, we go to the bottom left one here. So like I said, I got this note here. It says to make sure that the image on your sheet is horizontal. You could make one that works with vertical images just by applying the same sorts of principles. So we're only scaling by the height because it's a horizontal image. So that adjusts the thickness of the tail. The width we don't adjust because that would involve adjusting all the bone lengths, which we don't really want to do. That should already have been taken care of in the tailbone class. So we get the initial UV coordinates by taking where they start on the texture map, dividing it up by the texture width and texture height to get it so that it's in a 0 to 1 space. And we do that for the bottom right corner as well. And if we have any flipping going on, we can flip those coordinates with this. So this is going to be used as our, not really our V divider, I got UV divider, but it's basically the amount that we're moving the U1 and U2 to the left each time we go through a link in the bones. This here is half the height, so from the center joint we're going to want to measure up half the height upwards and downwards from there. Here I'm just deinitializing a couple of points. Point 1 is equal to the mouse probably when it's first passed in, and point 2 is going to be equal to the first bone's position, which will be to the left of the mouse coordinate. So technically this is kind of like your position 0, and this is more like your position 1. These others we're going to use, it's going to complain if I don't initialize them to 0. I set U1 instead of being where it was at the very beginning, based on the top left corner of the source rect, I'm going to set it to be the right side minus the division amount, and we're just going to adjust these two every time we go through links. So that's the sample source and the texture. Now, if this isn't the first one, and in this case it's not going to be, we're going to go to here instead first, and we're going to get the difference between the two positions to get the joint vector. So J stands for joint vector. And we're going to set the up vector to be the joint vector. We use this, we swap the y and the x, and we put a negative in front of the y on the front, and that makes it perpendicular. So it's a quick and easy way of doing a perpendicular without doing a cross product or anything like that. And we're going to normalize the length of that as n so that we have the direction in the up direction, and we're going to multiply that or scale it so that that vector pointing in that direction is the length of half the height, which we made here. So now that we got this vector pointing sort of upward from the joint, we create this vector up and vector down, VD, by adding the up vector to that point. And in this case, we subtract it to go in the opposite direction. Then we create a far up and a far down point by adding to the 2 points we made. We just add the joint vector to those. So if you understand vector math, you'd realize that all we're doing is attaching arrows to each other to get the resulting point that we want. AU and AD, I initialize them as VU and VD because on the first time we go through this, we don't have an average from before. So I is not greater than 0 the first time, so we're not doing this. So I put these O's in front of these to say this is the old version of the far up, far down, old version of the vector up and vector down. And I'm setting the old ones to be AU and AD. The first time we go through this, that's just going to be VU and VD because we set them here. The second time we go through it, I is going to be greater than 0, so it's going to reassign those differently. But you'll see when we go through the loop the second time here. It's just remembering what the average up and average down, which is averaging the two vectors. So we'll get to that when we go through it in the second loop. So we're going through the second loop now. I is not equal to 0, so we're going to get P1. P1 is the previous node. P2 is going to be the current node. So we calculate the new joint again. We do the same thing. We get the up, so we got that direction. We give it some length here, and then we add it on to where our current joint is. The joint on the right side, I should say, the joint position. And then to get the joint on the left side, we add the joint distance to the points that we just calculated here. So this time I is greater than 0. We set it here to be the average to be VU and VD, which are the ones on the left side. Or pardon, those are the ones on the right side. We add the old far left ones, or we add the old ones on the left side for the previous loop to the current ones on the right side and divide them by 2 here to get the average of them. And that way it kind of blends the two values together. Now we're ready to draw the quad. We have the AU, which is the upper left point, and it's kind of building the quad from the previous loop technically, because we weren't able to finish the ones on the left side until this loop because we didn't know where the average would fall yet. So now that we know the average, we can do the one for the previous loop. And so we go top left, top right, bottom left, and the usual UVs here. And now we're ready to move the U1 and U2 to the left by the U division based on how many bones we have. And again, we remember the values that we can continue the loop. When we're done, we still have to do the last quad because these are always one quad behind. So in this case, it's going to be the result of the far left ones here and the average ones that were created last time. The code is a bit confusing, and it's probably not essential to understand how it works, but it'll probably help you a lot if you do know how it works. You can play around with some of these numbers and fine-tune some things, as well as in tailbone here, how this drifting left and right works, how much the gravity works, the dampening here, the velocity, so it's 94% each frame. You can play with that stuff and see if you can tweak it, make it work a little bit better for your character. There's probably a few things we could do too to kind of smoothen out the mesh that's made so that it doesn't scrunch up at all. And you will notice that it does stretch and squash a little bit. That actually is deliberate. I actually wanted to do that. So another way you could do a tail if you wanted it to just flop right down, you don't want it wagging or anything, is you could use Verlet Integration. If you look up on the internet Verlet Integration, VERLET, and look up rope, you might be able to find some source code or at least some articles explaining how to make something like that. So for the grass, I actually changed things up a bit so that the grass are sort of in a thing I call Velcro chain. So all the bodies and joints are stored in here as lists, and I'm also keeping track of the vectors. So when I build it, I just pass in the world and the QuadBatch. When I make a grass chain, I give it a height, or width, a height, a starting position, number of divisions, the base body it attaches to, which in this case is going to be the big grass. I got no gravity set to true, but I think in here I might be overriding it, I'm not sure. And I'm not sure if you can tell much difference between whether it's true or if it's false in this particular case. So here I'm making grass chains and passing in width. I'm using the image width times 0.5, so the bounding rectangle is not going to be encapsulating the entire grass image because some of that's kind of see-through, so I'm going 0.5 to kind of make it a little more narrow and just giving it the grass height, the regular grass height. This is the start position of the base of the section of grass, and this will have 3 pieces that make up this piece of grass. And this is the body that it attaches to, and I'm saying no gravity is false, which means there is gravity applied in this case. Not that you can really tell much difference, so you could switch that back to true if you wanted, it wouldn't matter. And you can change the category here of what type of category your grass is if you want, what it collides with. If you want it to collide with a bunch of different things, you can use the OR and then go category dot, say, cat 4 or something. So you can add extra ones. We've got our dampening at 95% or 0.95, hertz at 16. And if you change these values, like this one, even this intensity one here, you'll notice that those are what mostly affects how floppy or how stiff the grass is behaving and how quickly it kind of snaps back into position and vibrates or whatever. So you can try playing around with those. I'm going to put this source code up probably on GitHub and leave a link in the description, and you'll be able to take a closer look at some of this and how it works. But there's a previous grass tutorial that kind of shows how the physics of this works. I'm not going to go over this in too much detail. If we come down here we're updating the grass, and then this loop, it's essentially attaching each segment to the previous segment and keeping track of the vectors, which is the difference between the mid position of that joint and the pivot, and then timesing it by 2 to get the actual vector that it's made of, which would be at 0, 0, 0. So I'm going to show you this draw chained grass thing, and I probably made it a little bit more bloated and complex than it needs to be. So you got this source here, the pivot base where it's going to attach to for drawing, and you got a list of the joints which we created here, these vectors it's going to be composed of. We can scale the width, we can do a sideways offset if we want to recenter the grass one way or the other a little bit more, depending, and that I added mostly because my images were a little bit off, and I realized after that really all I should have done was went into the graphics editing and just edited the image, so it kind of filled up the rectangle better. I've got tip scaling and base scaling, which are actually kind of handy. So the tips are going to be kind of transparent, the base may even be fairly transparent too, and so these can stretch the tip up and above where the physics would actually collide, so that really transparent stuff that probably shouldn't interact with anything, that stuff visibly goes up higher than where it actually would detect it, so that's what the tip scaling is for. Rotate base, I think, is a boolean here, and that is so if for whatever reason you decide to keep the base very stationary and solid, welded solid to the ground, you can do that. What I would do is I would actually leave this false or true and let it rotate, and just keep it behind the rest of the grass, like the other. Well, if I run it, you can see. So I'm kind of drawing this stuff first, and then I draw this thing here over top. If we go into QuadBatch class, the draw chain for this, the way that this works, it does all the usual stuff here. So what I did was I set J to be the first joint, and that's pointing up from the base, and UJ is the unit vector version of it, so it's normalized, and it's basically just has the direction. And then I set the base offset, so that's to stretch it downwards, to be equal to that scaled in the negative direction. And so the tip offset is that amount scaled in the vertical direction, upwards. So like before, we got these perpendicular vectors. There's a horizontal left and a horizontal right, and that's just the half width plus the horizontal offset and minus the horizontal offset for the other side. But to get the true horizontal, or to get the true left and right vector here, what we do is we take the left direction, which we calculated here, which is getting that perpendicular to the direction of the UJ, and we're scaling it by h right, which we made right here, and left for the other one. We're going negative left direction for that one. So if we're not rotating the base, then we can just add this essentially onto our pivot position, and we can do that for the left and the right. However, if we are rotating it, then we should give it the right and left vectors that we made here and add them to the pivot. So we've already calculated the bottom two. Keep in mind x3 is on the right, x4 is on the left. To get x1, we have to add to x4, and we add the joint vertex. So that's our joint vector, so that's effectively what we're doing here. It's like working with regular vectors, except we're doing it on just the x and y's by themselves without being in a vector. And we do the same thing with the we do the same thing with the other corners. With the bottom ones, we're adding on the base offsets to kind of stretch those down if we need to. I have this as add vertex. Let's rename this add quad. If this is the only joint, then we just add on the tip offset and make it the quad and return. And we loop the remaining bones here. And we start off by getting this position to be the pivot position plus the joint. So we're getting the next joint location that's what px and py is going to be. And then we're storing the old x3, x4, and y3, y4. The vertical division for the UV value for the V2 minus V1, just like before, we're moving those based on that difference divided up into the number of joints. So that's how big a piece of pie we're moving up. Each time we move through the bones, we start off by saying that the V1 value is going to be equal to V2 minus that amount right from the beginning. So we get the first joint, we get the normalized vector, kind of doing the same same as up there. We get the left direction, same thing as we did before to get the left and right, which we were doing here. And we're using that joint position and getting the new X, new Y, being that joint position that we made. Well, in the first loop we made it right here, which is the previous pivot position plus the joint. And we're saying that it's going to be that position plus the vector to the right and the vector to the left. So X4 and X3 are our bottoms, and what we're doing is we're taking the NX4 and NX3, which we made right here, and adding them to the current X1, X2, which before the loop we calculated those up here. So we're able to divide those by 2 and get the average. So we're kind of doing like we did with the tail, where we're kind of averaging those two vectors out to get the in-betweens, and then we can add the quad. So again, it's kind of lagging behind, adding the quad after it's done the math sort of thing, after it's done a loop. In this case, our first loop was kind of done up here, so we can add a quad right from the get-go. And we adjust our V coordinates for the UVs based on the division amount. If we're on the last one, we can figure out the tip offset based on the joint direction and the magnitude of the tip scale. And we can add in that tip offset. We're adding to N4 and N3 and X3, which are the bottom two, the joint distance, and then that extra tip offset. Otherwise, we just say that the top two, X1, X2, Y1, Y2, are going to be the bottom ones, NX4 and NX3, plus the joint distance. Then we can move from the current joint position to the next joint position by adding in that joint distance. And we can record the old values so that we can do our averaging for next time. Oh yeah, we need those old values for up here. Alright, and if we run it, this is what we get. What I would do is, well, there's actually a couple different ways you can scroll your world too. You can use the world matrix to pan around and just draw a span of what would be visible and keep track of where you are in the tiles, the visible tile section based on where the camera location is. That way your world coordinate, well, I guess it works both ways, it's just two ways to do the same thing. But you need your world coordinates for the Velcro-Physics. So everything's in world coordinates. So something could be 10,000 to the right and say 2,000 down. What we're doing when we're moving the player is we're going to be updating their world coordinate too. And we're going to be telling the physics engine that when the player's here, they're actually at location 10,000 and 3,000 down or whatever it is. And then that way the player can interact with the stuff that's there. So it's just a matter of converting your units from world space to screen space and back to world space, that sort of thing. As far as I know, I'm not sure how to make things collide the way you want them based on player positions. So if you have an absolute motion of your player in the world and you're not using physics or forces to move the player, one thing you can do is you can use fixed joint and have it so that it's always, instead of following the mouse position, it's following the player position, and then using that sort of body that's attached to that to make the collisions and force impulses and stuff like that on things in the scene. So that's an option, something to think about. So the Grass Physics one could probably use a little bit of work, a little bit of optimization. The tail one's actually really quick, and I don't think it needs any optimization really. It's pretty fast. Like, I could have hundreds of tails going around on here, and I don't think it would slow down at all. There's no physics interactions with these tails, but it wouldn't be too hard. I don't imagine it'd be too hard to add physical interactions with them, although I don't really see the use of it, so it's not personally something I would do. Just depends on your needs.